In this video and the next video, we're going to explore the stack and the stack pointer used in RISC-V. In this first part, we're going to find the motivation as to why we even want to use a stack in the first place. In the second video, we'll walk through several practice problems that'll give us a better feel for using the stack pointer in RISC-V. So the first question we'll ask is, why involve a stack in the first place? And the short answer is that the stack allows us to remember. What we remember and how we do it is the job of the programmer. Typically, we programmers want to remember the state, i.e. the context of a program, before we jump to other instructions. Let's look at a small example. Consider this function, and it doesn't really matter what it does. And then we have our main block, and main does a bunch of stuff, and then it makes a call to func. And then it does a bunch of other stuff. Now the question becomes, once we call this function and we jump to it, how can we ensure that once we get back from this function call, that all of our previous data remains intact? This concept of state means that we want to store the context of where we currently are and what we are doing in a program before we jump to the callee function. This ensures that when we return from whatever we needed to do inside of the function, we can continue the program's flow. Go ahead and erase this. So now that we have the basic idea that we know what we want to be storing, but what actually is state? Now it's important to note that the answer is more involved than what I will cover in this video, but I'll do my best to outline the necessary items. We can start by imagining when we would need to use the stack, what information we want to save. And these are just a few of the items that are typically stored on the stack. The first being the return address. When we make a function call, we want to be able to return to the address that called the function. Now, RISC-V has a nice register, the RA register, that handles this explicitly. But it's important to know that in many other programs, the programmer is responsible for pushing the return address onto the stack. So what's next? Well, we also have local variables. Each function may have its own variables, which should not interfere with those of the other functions. The stack keeps these locals during each function call. We also have the function arguments or parameters. And the final one that we'll cover is register states. Sometimes the state of a certain register must be preserved during a function call to be restored after the function call, maintaining the correct operational context of the program. Now that we have a general idea of what the stack is for and why we need it, let's walk through a small example of code and what the stack would look like through its execution. So I've gone ahead and written out an example problem. Here we have a main block that declares two local variables n1 and n2 and sets them to 1 and 2 respectively. And then we have an integer r result that we'll use to store the result of our add function that we passed n1 and n2. Then we'll print the result. If we look at our add function, it returns an integer, takes 2 arguments, and returns the resulting sum. Very simple program. Now off to the right, I've drawn what a typical memory layout would look like. Now while we are only concerned with the stack and the stack pointer, it's important to know that the heap exists and that the heap grows upwards and the stack tends to grow downward. This is the most common way you'll see memory laid out in most architectures. And I've just chosen an arbitrary address for the stack pointer, 2 to the power of 16, and it's -1 because of the 0 that we have down here. And 0 normally represents 0 or null. So the first thing that we make note of is that the stack always starts at the highest address in memory. This is why when we push to the stack, we want to decrement or decrease the stack pointer, the address that it's pointing at, because remember, the stack pointer points at an address in memory, and we can store at the address. So let's now go ahead and walk through this code and see how it would interact with the stack throughout execution. Something I would like to point out though is that in most programs you'll often see a frame pointer, and the frame pointer is just used, it's a register that marks the beginning of the function's frame or activation record. Now each function gets its own frame, and each frame stores the important information for that function. So for example, with main, we're going to store stuff like the locals, any parameters. Now when we call add, we're going to store the locals, arguments, and the return address. However, in RISC-V, they don't have an explicit frame pointer. However, if one is needed, generally from what I've seen, it's the S0 register that gets used. So let's start executing this program. Well, we start at main, so we're going to start building the activation record for main. This is also called the main frame. We're going to go ahead and store n1's value onto the stack as stack pointer. And now we want to move to the next local and store its value. So we have to decrement. Remember, we decrement because we want to go to a smaller address. But how much do we decrement by? Well, this is going to depend on the layout of your memory and the amount of bits you're using in your memory. For us, we're focused on RISC-32, so each of our memory stores a word or 32 bits. And the offset in RISC-V instructions is in terms of bytes. So we'll need to do 4 bytes, because 4 bytes, where a byte is 8 bits. So 8 times 4 is 32. Now if you were using a 64-bit ISA, your offset would be 8 bytes. Stack pointer -4, 4 bytes, and it brings us here. So we can go ahead and store R2, or N2, sorry, which is at the value 2, and then we'll decrement stack pointer again by 4 bytes. And going back to the frame pointer example, if we did have a frame pointer, it would be sitting right here. It wouldn't move until we call another function. It's not something that you need to know necessarily for RISC-V, but studying computer science, if you ever branch into compilers, it is something that will show up. So now that we arrive at the next instruction, we notice we have an assignment expression, where the assignment is based on the result of this function call. So now we need to set up the stack for this function call. So as we talked about earlier, some things we would want to put are the return address, the arguments, and the function's locals. Now let's just assume that this instruction is at address 3, so the return address will be 3. Now RISC-V has that explicit return address register, RA, but for this example, we'll go ahead and assume that it doesn't and explicitly push it onto the stack. So we'll push the return address 3, and we'll mark right here RA, and then we'll decrement stack pointer. And now we're at an open cell. And now that we have the return address, we're going to push the method's locals. However, there are none. So now we can go ahead and push the method's arguments. So we'll push N1. Now the important thing to remember here is that When we look at this instruction, we have two different values. We have the L value and the R value. The L value is associated with the address. So for example, stack pointer here would represent the address, while R value represents the actual data. So when we store this argument, are we storing the address of n1 or are we storing the value of n1? And the correct answer is we're storing the value of n1, which is 1. And then we'll decrement stack pointer and get the other argument, n2, which is 2. And we generally send stack pointer to the next available cell. And there's nothing here. So now that the function is set up, we can execute the function. And it's a really simple function. All we would do is collect the sum of both of its arguments and return that result. Now where would we store the result before we jump back to the function? And there are different ways you can do this, but for this example, what I would do is I would store the return address into another register, and I would overwrite the return address once I have it stored. That way, once I'm finished cleaning up the stack, I can easily just jump to the return address that I have stored in the register. And this way, I can just increment stack pointer and leave the rest as junk without having to clean it up explicitly. So what do I mean by this? So for this example, when we add a plus b, which is 1 plus 2, well, it just so happens to be 3, but I would explicitly do store word, and let's say I had the result in t0. I would store word where the return address was, which was stack pointer plus 4, 8, remember we're going by bytes, and 12. So 12 bytes away at stack pointer. And if t0 held this result, now 3 is here. Now we haven't updated stack pointer. We still need to clean that part of the function up. And remember, I have the return address in some register. Well, now that we're done with this function, we can clean up the stack. So for this example, simply all I have to do is increment stack pointer plus 12 bytes. And now you may be asking, well, what about this data right here? And the simple answer is that it's just junk. We don't have to explicitly remove it, which is nice. Instead, when we use stack pointer next, what we'll do is we'll just overwrite the data. So when stack pointer comes here, we would just write over 1. And this is no longer our return address. So let's say we finish the function call and we've jumped back to this instruction, and now the value gets stored as a main local inside of R, which it already is there. So then we'll just increment stack pointer, decrement. And when we write here next, we'll just be overwriting this junk. Now print is a function, and it too would create its own activation record. However, for the sake of this example, I just wanted to show how we would get the result from a function, use it later after cleaning up the activation records. Now, this was just for one function call. What about if we were using recursion, where we have functions calling themselves? And the idea is pretty much the same. As we call functions, we're going to store the necessary information on the stack and then create those activation records for the calling functions, the callees. And we will continue to do this until we reach a base case. Now, a common problem that you may hear is stack overflow. And this is where that comes from. The idea is that we keep putting activation records onto the stack, and the stack keeps growing down, but eventually it collides into the heap. And once we reach the heap and we try to overwrite that data, that's an illegal operation. So that's what's known as a stack overflow. So this is why having a base case is super important. Or even with a base case and having recursive calls that go far too deep will result in a stack overflow. And now that we have the motivation as to why we would want to use a stack, in the next video we'll go through several practice problems to get better practice and a feel for using the stack in RISC-V with the stack pointer register. I hope this video was helpful, and if you have any suggestions or questions, feel free to leave a comment down below and consider subscribing and liking the video. Until next time, thank you.